In our beginning discussion of arc length, we talked about finding a surface area by taking the arc length and just multiplying by the width of something. But in this situation, what we're going to actually do is we're going to revolve something. And so we're going to end up getting an area by the surface area of an object just by virtue of rotating that object about an axis. So we're going to talk about revolving again. But we're still talking about surface area. So in general terms, when we talk about the surface area of a three-dimensional object, we're talking about, let's take a three-dimensional object like a cylinder. We're talking about how much area is on the outside surface. It sounds redundant, I realize, but let's say if we were going to have to wrap this in wrapping paper. So we'd have to take care of the surface, the circular surface, the cylindrical surface here, and then we'd have to, and the one thing we don't do is we don't concern ourselves with the top and the bottom like we might do in geometry. So if you think about this, just the surface area here, really what we're talking about is lateral area. If you remember that term from geometry, that's just the sides. And so when we're talking about the lateral area of a cylinder, we're talking about taking this curved surface here. And if you remember back from geometry, we could cut that curved surface and unroll it, and it would just become a rectangle. And that rectangular surface, then the length of the top is going to be this distance around this curved surface. So that's going to be 2 pi r, or the circumference of that circle, where the radius is from the center to the outside. And of course, the height here is just the height of the cylinder. So that's your typical lateral area problem for geometry. So how we kind of give this a calculus spin here, not to be punny, but let's just say we have a line here. So let's just kind of throw a line up on the page. So here's a line. And let's say we want to revolve that around the y-axis. So when we're looking at this, if we're going to revolve this around the y-axis, let's not take the whole line, let's just take this part of the line. So if we revolve that around the y-axis, we end up with, something that looks kind of like that. And of course, you might recognize that as kind of lampshade shaped. And so the surface would be that fabric on the lampshade. And so if you notice then, the sloped portion of the lampshade is nothing more than the arc length, or however long that portion of the function is. So that's why we have something that looks like our arc length expression in these calculus expressions. So here's our arc length. And the geometric equivalent would be the height here. That would be the side of the lampshade. So this arc length here would be that arc length expression. And then if you notice, as we, instead of just having vertical slides like we do with a cylinder, we have these slides that have slope. And so we have a smaller radius on top and a larger radius on the bottom. And so depending upon where you are then, if we're integrating from point A to point B here, depending upon where you are along that function dictates how big your radius is going to be. So at the top here, your radius is going to be smaller than at the bottom. So your radius is a function of x. And so that radius function has to be displayed here. So here is your 2 pi r, which is the top of your cylinder. And then here is your height of your lampshade, which is the height of the cylinder. So you end up getting an expression that resembles the lateral area like we would see it in geometry. For this problem, we're going to find the surface area generated by revolving this function about the x-axis. So in this situation, we're going to rotate this about, there we go, the x-axis here, and we're going to go from 4 to 9. So we're going to start at 4 and at 9. And if you notice, those two values are perfect squares, so they work nicely in that function. So we're going to take this surface and revolve it about the x-axis. So we're going to get that shape that kind of resembles a lampshade again. And so so we're going to have to get an expression for the arc length, which means we need the derivative of this function. So let's find that first. So we're looking at the function, I'm going to rewrite this function as 2x to the half power. Then that makes it easier for you to maybe see the power rule here. So the derivative then is 2 times a half x to the minus 1/2 power. And simplifying that, you get 1 over the square root of x for the derivative. And then we're going to revolve that around the x-axis. So our radius, since this is our axis of rotation, our radius is going to go from the axis of rotation up to the function. And so that's going to be our r of x. And so that r of x then is going to be the function itself. Because, you know, the value of the function is the distance it is from the x-axis. So the r of x is going to be 2 times the square root of x. And so as we set this up then, for our surface area of revolution, we're talking about integrating from 4 to 9. And we have our r of x here, so we got 2 pi r of x. So I'm going to squeeze that 2 pi out in front. Our r of x is 2 times the square root of x, and then times our arc length. And of course, that arc length expression is 1 plus the derivative squared. So we're going to have to square that. And I'm just going to simplify it. That's a multiplication sign right there, by the way. So I'm just going to simplify that. And I'm going to use the f int capabilities here, just because of the complexity of the integral. So we have 2 times the square root of x times the square root of 1 plus 1 over x dx. And so that's what we have to integrate. And you could probably integrate that by hand. It would be pretty complicated though. So we're going to go ahead and use the graphing calculator again. And like I've done several times in the past, I'm going to go ahead and identify our y1 and our y2. And so let me just come back here and note that I'm going to call this y1, and I'm going to call this y2. And that's not a bad annotation. Whoops. That's not a bad annotation to do when you're taking an AP test, because this is pretty common notation. The grader will know that that you're using a graphing calculator here, and this is putting a function into the graphing capabilities. So I'm going to go ahead and type in 2 times the square root of x. Oops. Try that again. 2 square root x. Okay, and then in y2, square root 1 plus 1 divide x. Okay, so there are the two functions. And then again, since those are in functions, we can use our vars key to get those functions in the integration expression. So I'm going to go math 9, that's our f int. And then in the integral, I've got y1 times y2. So I'm going to put that in my expression over here. So we've got our f int. I'm going to go into vars, select y vars, select function, and then select y1, and then times, and then repeat that process, go into vars, y vars, select function, and select y2. So there's our y1 times y2, that represents 2 times the square root of x times the square root of 1 plus 1 over x. Variable of integration is x, and we're going from 4 to 9, so 4 comma 9, and again, like I've said so many times in the past, this is just the integral, so we do need to remember to include the 2 pi in our answer, and so we are getting an answer of 27.257, appropriately rounded. So this is 2 pi times 27.257. I'm going to go ahead and multiply by 2 pi times 2 times pi. As long as it's a decimal that appears to be irrational. So the surface area then for this, this revolved function from 4 to 9 is going to be approximately 171.258, again rounding to 3 decimal places, square units. Remember, it's area, so it's square units. Example, we're taking an inverted quadratic or parabola, and we are going to rotate this about the y-axis. So we're going to go ahead and rotate this about the y-axis here, and we're going to go from 0 to 3. So it looks like we're taking the function from 0 to 3. And so we're taking this portion of the function and spinning it around the y-axis. Okay, and so notice we don't have to go from -3 to 3 because that would be doubling up. And so you'd get twice the surface area. It'd be like painting it twice. And so if we revolve this around the y-axis, then we get, you know, this thing that's closed at one end, so you could call it a bowl or something like that. And so again, it's an arc length problem, so we do need the derivative of this function. So let's go ahead and get that. So the function is 9 minus x squared. Using the power rule, the derivative of this is 0. Derivative of this is minus 2x. So there is the derivative of that function. The r of x is going to be this value here. And that r of x is, from a Cartesian coordinate standpoint, that r of x is just the value x. It's just the x coordinate of the function. And so when you have things revolved around the y-axis, it's kind of a nice break. You just can throw in the value x for the r of x. And so, so we have, for the expression of our surface area, we've got 2 pi. Integrating from 0 to 3, our r of x is just the value x. Our arc length is the length of that green curve, and that is 1 plus the derivative minus 2x squared dx. And you might notice that the derivative is negative, and you know that because of this this shape here. That doesn't surprise you, but when you square it, you get a positive, which should reinforce the fact that length is always a positive value. You should really never have a negative in that expression because of that, the definition of length. So kind of keep that in mind. If you start ending up putting minus signs somewhere and you're doing an arc length problem, that should be a red flag, because length is always positive. It just means you squared something incorrectly. So squaring this, you get positive 4x squared. So 1 plus 4x squared. And this is a basic u sub. You can do a u sub here. In fact, let's just kind of talk about that for a second. If you do a u sub, and the sub you do is 1 plus 4x squared, then the derivative of that is 8x dx. So we have an x dx to factor out. So this is just a 1/8 du equals x dx. So we're looking at then from a u sub standpoint, this being, we're going to substitute out the x dx for 1/8 du, and this now becomes the square root of u, and of course there are new limits here, and I'm not going to go into what those limits are. It looks like, well, actually I guess I will. With x equal to 0, u would be equal to 1, and with x equal to 3, u would be 3 squared is 9, 36 looks like 37. So from 1 to 37. So you could integrate that easily enough. So this is definitely something you could do by hand. Okay, and you would be expected to be able to handle something like that on a non-calculator part of an AP exam. For the sake of time here, I'm just going to go ahead and throw this into an fint, and I'll do it the old-fashioned way. I'll go ahead and throw everything right in there. So I have x times, let's get a time sign. No, there we go. X times the square root of 1 plus 4x. Close off that bracket. Variable of integration is x, and I'm going to go from 0 to 3. There we go. And so that again represents just the integral, and we're looking at 13.297. So this is 2 pi times 13.297, and if we multiply by 2 pi, we get 83 points. Oh, we get 83.54, which is wrong. Actually, I'm going to keep this here because I'm so close to the end anyway. Can you see my mistake in the graphing calculator? Very common mistake. So let me put a red X through this because that is incorrect. But I just want to point out really common pitfalls here. If you come over here and you notice, I put 4x in here, and I should have put 4x squared. So if you notice, I need a power of 2 next to this x here. So I'm going to go ahead and hit second entry until I get that expression for fint back, and I'm going to backspace to there. And in that location where I need a squared, I'm going to hit insert, and I'm going to insert a power of 2. So there's my 4x squared. So that's, again, a very common mistake you're going to run into, and you're going to make it yourself from time to time. So that integral really is 18.67. So it's 2 pi times 18.672. And then when we multiply by 2 and by pi, we get an area of 117.319, appropriately rounded square units. Past problems in dealing with surfaces of revolution, but certainly one that College Board would expect you to do on an AP exam, and that is confirm or verify a formula that you know from, in this case, geometry. So if we take the semicircle here and revolve it around the x-axis, we create a sphere, a hollow sphere. And from geometry, you might remember that the surface area of a sphere is 4 pi r squared. And so if we have a general equation for the semicircle, which we have here, we know that the general equation for a circle is x squared plus y squared equals r squared. That's in standard form, of course. And you might look at that and say, hey, it's the Pythagorean theorem, and you're right. That's all the equation of a circle is the distance, because the definition of a circle is the distance from the center to the edge is constant value of r. And if you notice, if we draw that line from center to edge, we get the hypotenuse of a triangle. So the equation for a circle and the hypotenuse, or the equation for a circle and Pythagorean's theorem are really one and the same expressions. And so if we solve this for y, we get this expression here, the square root of r squared minus x squared. And so if here is our function, and we revolve that function around the x-axis, we're going to make that square, or we're going to make that surface area, that spherical surface area. And so we should then be able to get this expression if we just go ahead and integrate the arc length times the r sub x function. And so, of course, to do this, you need to have the derivative of this function. And the derivative of this function is a little complicated, but not too bad. So looking at this function, we have r squared minus x squared to the 1/2 power. And so taking the derivative here, we have 1/2 r squared minus x squared to the minus 1/2 power. And don't forget about the chain rule, times the derivative of the inside. So times minus 2x. And so simplifying that, we have minus x over the square root of r squared minus x squared. So there's the expression of the derivative. And I'm going to go ahead and simplify this a little bit. Before I throw it in, I'm going to go ahead and square it. So the derivative squared is this squared. And remember, it's going to be positive. So it's going to be x squared. I squared the top. Squaring the bottom just gets rid of the radical. So it's going to be r squared minus x squared. Okay, so there is the expression for the derivative squared. And the r sub x function, if we look at this, again, the r sub x function is measured from the axis of rotation up to the surface that's being revolved. And so this r sub x function is just the value of the function itself. So it's just the r squared minus x squared to the 1/2 power. So that's the r sub x function. So putting this into an integration expression is a little bit daunting, but it's not too bad. So we're looking at a surface area expression here of 2 pi. R sub x is r squared minus x squared, square root, and times the arc length. So the arc length is 1 plus the derivative squared, which is this expression right there. X squared over r squared minus x squared. And then the limits of integration, you're going to have to integrate from here, and it's kind of off the picture, all the way to here. So depending upon the function, that's just going to be minus r to positive r. So it's going to be minus r to positive r. So there's the expression. And this looks a little scary, but it really ends up being not too bad once we simplify it. So from minus r to r, and I'm going to go ahead and get this as one fraction. So I'm going to leave this alone. R squared minus x squared, let me correct that. R squared minus x squared, square root, times, and I'm just going to kind of do a quick and dirty simplification here. This, of course, is r squared minus x squared over r squared minus x squared, right? That's the way of writing 1, plus x squared over r squared minus x squared. So we have common denominators now, but we can add those two fractions. So when we add the numerator here, r squared minus x squared plus x squared ends up just being r squared. And then the denominator is, r squared minus x squared. And of course that's all under a radical. Can't forget that, that's pretty important. So that ends up being, writing it as one fraction ends up being that expression right there. And so looking at this then, you can already start to see that we can of course put a radical on the top and a radical on the bottom. These cancel, right? So if you don't see that, I'll write that step. We have r squared minus x squared, that's our r sub x function. And then we have the square root of r squared And then we have the square root of r squared minus x squared. Okay, so like I said just a few seconds ago, those two cancel. So really what we're left with is integrating 2 pi from minus r to positive r. And the only thing left here is r. And of course, this is all dx, right? This is all a dx problem. Shame on me for dropping that differential expression off all the whole time here. So that's all a dx. And that's really important because we know r then in this function is nothing more than a constant. So really what we're doing is we're just integrating. We can pull the r out, it's just a constant. We're just integrating dx. And of course, integrating dx is pretty darn easy. That's just x from minus r to r. And so when we substitute in, we've got 2 pi r times r minus a negative r. And then simplifying, we can see that this is just 2r. So we end up with the expression 4 pi r squared, which is the surface area of the sphere that you learned in geometry.